section 8.2, graphing simple rational functions. We're getting out of our exponential and log world for a little bit and then taking a look at what happens when we have the quotient of two polynomials. These are some unique looking graphs, and because of that fact, we are actually going to be going back to our world of just generic coordinates instead of critical movements, which means we're not going to talk so much anymore right now about parent functions, although with some very simple rational functions you can implement the whole concept of parent function of movements, but we are going to put that off on the side for right now and think about coordinates instead. In the process of doing that, when we graph these rational functions, there really is one critical piece that helps us develop our t-tables that we then use to draw the points for these graphs, and that is the vertical asymptote. So these graphs are going to have some asymptotes associated with them, and how we find those asymptotes will be dependent on the type of rational function that we are dealing with. Rational just means we've got a quotient of polynomials. And if in a polynomial that happens to be in the denominator, if we have variables down there, we have to be aware of what the variables would produce a 0 in the denominator. And if that were to be found, then we have found what is known as a vertical asymptote. So we've talked about asymptotes before. They are these lines that our graphs approach and get closer and closer to. So here we go. Here's our first one. We just take, again, the idea of rational function just being a quotient of two polynomial p of x, q of x. Here we see a little visual. And again, parent function is used here. Simple rational function of 1 over x. Here's what that graph would look like. Now the green dashed lines you see there represent our asymptotes, and we want to make sure we include these when we draw these rational function graphs. How we find them? Well, 1 over x. If you think about values of x that produce a 0 for rational functions, in this simple case, we know that x cannot be equal to 0. If it was, I would be undefined at this function. So we look for the vertical asymptotes in our denominators, and in this case, if I were to set the denominator equal to 0, I would have a vertical asymptote of x equals 0, and that's where that green dashed line is coming from. What about the horizontal asymptote? Well, if we think about, is there a way for me to make f of x equal to 0? Is that possible? Can we get this thing equal to 0? If I'm looking at my 1 over x, and I think I can't put an x of 0 in there because it becomes undefined, and any other value of x, a negative value, a positive value, a decimal value, there's no way for me to make f of x equal to 0. It's just not possible. And so because of that, because it's not possible to make f of x equal to 0, that's what determines our horizontal asymptote. And then we get these sweeping curves in here, which are known as branches. That's what these guys are called, branches. There's one there, there's one there. And you draw them from plugging in some x's and finding some y's. And that's what we're going to look at here for this. So let's look at some simple rational functions here. Our first one, y equal 4 over x. All right, there are a couple steps we're going to take into consideration. And since our coordinates that we base our graph off of are determined from our vertical asymptote, maybe the first thing we think about finding, step 1, is find the vertical asymptote. Vertical asymptote, we're just going to abbreviate it VA here. And how we find that is you look in the denominator. That's where you'll find it, and you make it equal to 0. And solve for x. So in that case, x equals 0. There's our vertical asymptote. So we'll go ahead and put that vertical line in here at x equals 0. Our second step, let's go find the horizontal asymptote. And in this simple case, our horizontal asymptote is always going to be 0 because there is no variable in the numerator here. So for just the discussion point right now, we're just going to say y equals 0. Now we'll highlight some ways of finding horizontal asymptotes. But first, let's draw our horizontal asymptote of y equals 0 in. Okay, going back to the horizontal asymptote discussion. Again, we're doing this for a simple case where we have a constant in the numerator and a denominator that has a variable. In that case, y equals 0 all the time. In other cases, what we do for finding horizontal asymptotes, let's give ourselves a couple different examples. What if we had a to the m over b to the n? And in this example, we can have a couple different cases. Let's say case number 1. What if the power of m is bigger on the numerator side than it is in the denominator side? When this happens, when your power of m is bigger, then that means you have no horizontal asymptote. It doesn't exist. And again, thinking about why this is the case, if I had, let's say, x to the third, for example, over x squared, every time I put bigger and bigger values in for x, my numerator value gets larger, my denominator value gets larger, but not quite as fast, and I'll never be approaching this value of y equaling something when the numerator on the top is always getting bigger, faster than the numerator on the bottom. So in this case, no horizontal asymptote. Then we can have a second case where what if the numerator on the top is actually less than the value, I'm sorry, the power on the top is less than the power on the bottom. And again, we're talking about degree of the function when we're mentioning power. So the degree of the function is what we're talking about here. Degree on the top is smaller. In that case, we get a horizontal asymptote of y equal 0. And that was kind of what was going on here with our generic 4 over x. So we have a 4, which is a constant, no variable up there at all, so no power to contend with, over an x to the first, so our degree on the denominator was actually 1, and our degree on the numerator was nothing. So we have a smaller value of m power, and we've got a value of y equals 0 because, again, in this case, the bigger numbers I put in for x, let's say I put 1,000 in there, 4 over 1,000. Well, what if I put 10,000 or 1 million or 100 million? 4 over 100 million, we're going to get a decimal value, y equals 0.00000 something. And it seems as though our y values will continue to get closer and closer to 0, but actually never be a 0. So there's the condition there for when y is equal to 0 for a horizontal asymptote. And then let's finally look at, well, what if the degrees of the function in the numerator and the denominator are the same? So power of m equals power of n. In this case, your horizontal asymptote will be the ratio of your coefficients. So y would equal, in this case, for our example, a to the m over b to the n. Our horizontal asymptote would be a over b. So those are 3 of the conditions we can have for some of our rational functions for finding horizontal asymptotes. For vertical asymptotes, we will always just set that denominator equal to 0 and come up with that value of x. All right, what about the table now that we use to generate these movements, or these coordinates? What we do when we're going to plot plotting points for rationals, are some steps to think about. Step number one. Well, yeah, we'll just call it step one. Locate the vertical asymptote. And then choose for your table values of x that are left and right of that vertical asymptote. Pick some values of x that are left and right. And specifically, I would always consider values farther away and closer to. So far away from the vertical asymptote and closer to it, right next to it. This gives us an idea of what's going on with the branch. So let's see how that plays out here with this function we have. We'll go ahead and we're doing y equal 4 over x. And we're going to pick some x values and find our y values that we can draw our branches from. Okay, our vertical asymptote is located at x equals 0. So we're going to pick points. We're going to choose values of x that are to the left of that and values that are to the right of that. And we're going to pick values to the left. My recommendation is wherever your vertical asymptote, pick the coordinate that's immediately to the left of that. So in this case, an x equal -1 would be a good testing point. And then let's pick one that's a little further away. So maybe let's test x equal -8. Again, the further away is going to help me see what the branches are doing next to the asymptote, the horizontal asymptote. The points that we choose that are closer to the vertical asymptote, in this case -1, are going to show me what the branches are doing next to the vertical asymptote. So further away gives me ideas next to the horizontal asymptote. Points closer to gives me a shape of what's going on next to the vertical. Then we want to do the same thing on the right-hand side. A point right next to the vertical asymptote so I can see how we're approaching the vertical asymptote. So in this case, 1 is right next to the vertical asymptote. Now a point further out to the right from the vertical asymptote. And let's test 8. This is going to give me an idea of what's going on as we approach the horizontal asymptote. So those are the points I'm going to choose. We plug them in. -8. 4 over -8 is -1/2. Plug -1 in, -4. +1 in, +4. +8, 1/2. Those then become my coordinates that I'm going to plot on my graph. So -8, -1/2. There's -8, -1/2. -1, -4. +1, +4. +8, +1/2. Then I just simply graph got disconnected here. Then I just simply connect my coordinates. Again, approaching the asymptotes, I can see that my branches would look something like that. Let's try something with a little. You guys can go ahead and try this one. Again, here's where you might pause, try your points, test your coordinates based off of your vertical asymptotes, find your horizontal asymptotes, and see what you get, and then come and check in. I'm going to put the answer up here real quick. Vertical asymptote wise, horizontal asymptote, the degree on the denominator side is less. So we put in our horizontal, put in our vertical, graph this thing. Something like that. Okay, so those are our simple cases, simple hyperbolas. Let's move on to something where we get some translation involved. So graphing the translations of simple rational functions. So in this text here, they're using the variables h and k. They've been using that throughout to talk about left-right horizontal with left-right translation with the variable h, and up-down translation with the variable k. We have introduced a, b, c, d. So these h's, that would be like my c value, and this would be like my d value. So I could come in here and make these c's and d's. That's my c. That's my d. That's d. That's c. Just to kind of follow the notation we've been using throughout this course. All right. So you'll notice that this exponent, or this rational function, looks a little different. C, D. It's got down in the denominator a binomial. And then, separate from the quotient part of the rational function is this constant that in this case is being added, but it could also be subtracted. So what happens here for our horizontal and our vertical asymptotes, it's a little different rule for the horizontal piece, not so much for the vertical part, but horizontal asymptotes are simply, in this case, the value of d, or k. So here we do the same things we've done before. We draw our vertical asymptote. How do we find our vertical asymptote? X minus h equals 0. So solve for x, you get x equal h. In this case, if we're using our variables again, x equals c. Horizontal asymptote is just the d value, so y equals d. So now I don't have to do any of that testing where I was worried about the degrees of the function in the top and the bottom, because I've got this constant that's happening out there on the right-hand side. Now, the values of the vertical asymptote and the horizontal asymptote, their equations, they intersect each other. That value of hk, or that value of cd, becomes that intersection point. So my branches are going to be following along within the limits of those two asymptotes, vertical and horizontal. I test points to the left of the vertical asymptote, one close to, one further away. I test points to the right of the vertical asymptote, again, one right next to it, one further away from it. And I get my same idea of these branches that were shown. So let's try it here with this example. Vertical asymptote, find x minus 1 equals 0, therefore x equal 1. Or again, just the opposite, right? The opposite of what I see going on down here. So there's my vertical asymptote, x equal 1. My horizontal asymptote is this value of d. So in this case, y equals 2. So I have my two asymptotes. I can put them in. Y equal 2. X equal 1. My branches will fall within the areas that are bound by those asymptotes there. And then test some points. So again, based off of the vertical asymptote. So my vertical asymptote being 1, I'm going to test a point further to the left. So let's test a negative 8. And then let's test 0, which is the point immediately to the left of the vertical asymptote. And then I'm going to test a point immediately to the right, so I'm going to test 2, and then maybe a 10. All right, we put these coordinates in. These are not movements again. These are coordinates now coming from the origin 0, 0. Put a negative 8 in. You get negative 3 over negative 9, which is 1/3. And then 1/3 plus 6/3 thirds is 7 thirds I have. So 2 1/3. Put a 0 in there. You get negative 3 over negative 1, which is 3, and 3 plus 2 is 5. Put a 2 in for x. You get negative 3 over 1, which is negative 3. Negative 3 plus 2 is negative 1. Put a 10 in for x. You get negative 3 over 9, which is negative 1/3, plus 6 thirds is 5 thirds, which is 1.67. All right, we plot these points. So negative 8, 2.3. Getting right next to that horizontal asymptote. 0, 5. Again, next to the vertical asymptote. 2, negative 1. 2, negative 1. Next to that vertical asymptote. 10, 1.67. Next to that horizontal asymptote. And there's our graph. All right, let's give this one a shot, or you give this one a shot. Go ahead and put it in here. Points. Negative 10 in, negative 4, negative 2, and maybe a 5. And I test those and come up with my coordinates, and then connect those coordinates, and there's my graph. All right, moving on to the next type of rational functions. We've seen a simple one. We've seen one that involves translation, left and right and up and down, which basically just means the asymptote location is different from your zeros. And then you have situations like this, where we have got a binomial divided by a binomial. These two happen to be both linear. And this is kind of going back to when we were introducing specifically how do we find horizontal asymptotes. This is kind of going back to that first example we looked at, where we saw our 3 cases based off of the degrees of the function. So that's what we're going to use now. Now you'll notice in the vertical asymptote how they're determining it. They have this equation, x equals negative d over c, and it looks fancy and everything, but really all you did to get that, it's what we've been doing all along. Take your denominator, set it equal to 0, and x would equal negative d over c, which is where that's coming from. And y equal a over c. So for the horizontal asymptote, where does that come from? Well, we have ax plus b, cx plus d. The denominator and the numerator are both powers of 1, so you have a situation where your degree of functions are the same thing. And we said that the horizontal asymptote is just the coefficient in front of those, so that's where that is coming from. So let's try that now here with these graphs. So a little different than finding our horizontal asymptote. Again, not any different finding the vertical. So vertical would be x equal negative 2, because I said x plus 2 equal to 0. Okay, our horizontal, though, I have degree of 1, degree of 1. So my coefficients of 3 over 1 would be my horizontal asymptote. I want to get rid of those. People might think it's the power of 0. It's just indicating that the powers of those are both 1. linear. All right, so put them in. Vertical at x equal -2. Horizontal at y equal 3. There we go. Testing some points. Okay, we look at our vertical asymptote to determine what x's I'm going to use. And let's say we did a, let's just do a negative 8 again. And then -3. And then -1. And then maybe 6. Plug them in. -8. If I plug a -8 into the top, I get -24 minus 6. So -30 on the top. -8 on the bottom. -8 plus 2 is -6. So -30 over -6 is a positive 5. -3 on the top makes -9 minus 6, which is -15. -3 on the bottom makes a -1. So -15 over -1 is a 15. -1 on the top makes -3 minus 6, which is -9. -1 in the denominator makes 1. So -9 there. 6 makes 18 minus 6, which is 12. And 6 plus 2 is an 8. And 12 over 8 becomes 4/3. Okay, I have my points. Let's plot them. -8, 5. -3, 15. Well, it's putting me off of my graph scale here. So I just know that that's the point that's going to be approaching my vertical asymptote there. -1, -9. 6 and 4/3, so 1 1/3. There would be my points. And there is your graph. All right, your turn again. Picking points to the left, picking points to the right. So here's some application to where we might find some rational equations, rational functions at work. We've got our phone bill. Company charges us $65 for installation and then a monthly fee of $32. And we're letting X represent the number of months of our phone service. And our first two parts here ask us to write equations. One of those equations is a total cost. This would be how much I'm going to pay for the life of my phone service. And then the next equation asks us for an average cost on a monthly basis. So the longer I hold on to my phone service, my monthly cost will adjust. Why is that the case? Well, maybe we should start out with the first equation. We've got an installation fee. And an installation fee is a one-time deal. You don't have to pay that more than once. Then we have a monthly fee. That's happening on a monthly basis. So every month I'm going to have to pay my $32. So we have X representing how many months. We have a monthly fee of $32. So my equation for cost would definitely have to include that monthly charge. But it also includes the $65 one-time fee. And then I can find, if I held onto my phone bill service for, if I owe my phone service for 20 months, for example, I could put a 20 in there, multiply it by 32, add $65 installation fee, and there's my total cost for the 20 months. That's probably the easier of the two equations. In fact, most of us come up with that fairly quickly. It's this next one here, where it's asking us for an average per month. That might be a little tricky. Well, maybe we first talk about what an average is. Remember that an average is equal to the sum of all of your data, whatever that might be referring to, over the number of items that you're adding together. Well, our sum is equivalent to our total cost. And we're doing this for X number of months. And so our equation can then be that the average monthly cost is equal to our 32x plus our 65 divided by our x. So you can see, you can try a couple of different points here and see what's going to happen. So 1 month service is going to be $97. 32 times 1 plus 65 over 1. 97 bucks. If I went for 2 months, though, I'd have 68 plus 65, and that's 133 divided by 2. And that number is less than my 97 for an average monthly cost. And so you can see the more value I put into x, the larger that x value gets. I'm going to have a situation where my monthly averages drop. But they can't drop forever. But let's see what the graph looks like first of all. So here we have our equation. And we have in this equation, obviously we've got some asymptotes. We've got a vertical one where x equals 0. Well, that makes sense. We're talking about months, and we can't have negative months. But we also have a horizontal asymptote. And this is the one that we're interested in. So our horizontal asymptote, we look at the degree of the function in the numerator, which is a linear 1. The degree of the function in the denominator is also 1. So that means I'm able to take the coefficients of the numerator and of the denominator. So I get 32 would be my horizontal asymptote for this thing. So we put in our horizontal asymptotes. We're going to just eyeball it here. Say it's right around there. We know our vertical asymptote is right down the axis line here. So even though we have a rational function that usually generates these branches, and they're usually in like diagonal relationship to one another, but not always. I'm only going to focus on one of those branches because I'm not going to deal, again, the application now applies to the fact that I can't have negative months. So I'm only going to be dealing with positive months. And if I were to graph this thing, I would get that. Plugging in some x values, I'm going to plug in 1 and maybe 15 or something, a couple points. I know it's a branch, so it's going to have this sweep look to it. But why this 32? What's the significance of the 32? Well, the asymptote. We're trying to find our average monthly cost. The longer I hold on to this phone service, the closer I'm going to get to just simply having an average monthly cost of the $32. The $65 initiation fee or installment fee over a course of a long period of time is negligible for my monthly costs. So that's what that horizontal asymptote is representing. I can't go below that. I'll never actually equal to $32 per month for my monthly cost because I had this initial installment of $65 that I began with. So that's always going to play into my total monthly cost. average monthly cost, sorry. All right, then what do I do with this graph? Well, like any good graph, you can interpret information off of the graph rather quickly, but it might not be exact. So in this case, how many months until our average is 33.25? Well, in our graph here, I don't think we're quite long enough out in the x direction to physically see it, but if I was, I could project a horizontal line over from where $33.25 was represented on the y-axis, intersect my graph, and then drop a vertical down from that point to find out the number of months. But probably the better way of coming up with this is to simply, if y is representing my average cost is supposed to be $33.25, then I know that I can just set up my equation like this. And then I'll get 33.25x is equal to 32x plus 65. And then I get $1.25x is equal to 65. And then I simply divide my 65 by $1.25, and I'll find out my number of months. And I'm 52 months away from an average of 33.25. So there's an application for our rational equations. Hope that was helpful.